Hi, welcome to the next Entagma tutorial. Today's topic is Heightfields. Heightfields were added to Houdini 16, and they are basically a procedural world-building toolset. Very similar to World Machine, if you know that. It's fun to work with these, and today I not only show you how to create a terrain from scratch, but I show you how you can render this live in Redshift. And that is something special because Redshift does not support rendering of 2D volumes. But by making a little detour, we can make them work in Redshift directly. So let's just dive into Houdini and start. Just lay down in the scene context a Heightfield object. Like so, and this comes predefined with a Heightfield. Inside you find a Heightfield node. Let me make the parameters visible, and you see that this Heightfield has a size of 1000 by 1000 units. Size doesn't matter in Houdini, so by any means try to model real-world sizes. And by default, one Houdini unit resembles 1 meter, so this is 1 kilometer square, which is good. The second important parameter is the grid spacing, because this determines the resolution of this huge terrain. If you middle click on the node, you see that this is actually a volume, a 2D volume to be precise, with 500 by 500 subdivisions, so it's 250,000 voxels. And that is due to the grid spacing of 2. Heightfields work with 2D volumes. And what 2D volumes are? Well, basically, they are images. Images storing one float value. And they probably decided to implement this in the SOP context using volumes due to performance reasons, just because Heightfields is mainly implemented in OpenCL, and you can do that easily in Houdini in the SOP context. The COP2 context that deals with images is single-threaded and does not use OpenCL, so probably this is a cause. Before we start to shape our terrain, let's investigate a little further. Right-click on this Heightfield node and state Allow Editing of Contents. Now dive inside. And you see that this terrain is really nothing but two 2D volumes. So if you click one, you see it's just a standard Houdini volume storing the height, and then the second one storing a mask. And this mask can be used to do different effects later on. And the only thing that is really different is the visualization. So in Houdini 16, a new display mode for volumes was added, the display mode Heightfield. So instead of smoke, you can visualize this as a Heightfield, which actually shows you the surface and the displacement. And this volume visualization is in charge of putting the mask as a color on top of this. So basically what Heightfields are, it's basically a collection of 2D volumes, and you can have more masks than just one. And all of them come out of this green port. All the Heightfield nodes use this green port to indicate that this is a compound data type, so to speak, consisting of different 2D volumes. And now let the fun begin. Lay down a HF for Heightfield and then noise. Heightfield noise. And wire this into the noise. Make this visible, and you instantly get a nice noise effect. You can state the noise type, and I want to go with simplex because it gives very natural terrain results. I want to model a mountain in the middle of my terrain, so let's do a little bit of offset here. Say 390 and minus 380. I found these values beforehand, and they give a nice mountain here in the middle. That's what I'm after. And now I plan to do a second terrain and then blend the two, because I want this mountain to be the main elevation and then everything else to be flat, basically. So let's do a second Heightfield noise. Here. Like so. Keep this on sparse convolution and just lower the amplitude to, let's say, 175. This is just to give the ground a little bit of detail. Now we have two terrains. One very flat and one with mountains. Let's blend the two. But before we do that, we want to alter the size of this mountain here. So let's append a Heightfield remap. Heightfield remap. This is basically a fit range, but for Heightfields. And you can press the compute range button, which gives you the current elevation, which goes from minus 200 to 158 meters. And now you can change this. Let's say to minus 100 and 100. Minus 100 and 100, like so. A little bit more realistic elevation for hills. And now we can use a Heightfield layer to composite the two. So put this in the first port and this in the second port. This Heightfield layer is basically a compositing operator. And here is a compositing operation. At the moment it's replace, so the input 2 is replacing input 1. But if we set this to maximum, we get the maximum value of both ports. And this is exactly what we are after, because now I have this mountain here in the middle and flat ground everywhere else. The transition between the mountain and the ground is a little bit sharp for my liking. So let's smooth this out. And for this we will use a mask. So let's put down a Heightfield mask by feature, because this is a very versatile node to generate different masks. And we want to mask by height. So tick off mask by slope and tick on mask by height. And this allows you to just select the height range to mask. And our height range should start at 0 to mask basically everything. But because of this remap curve here, the values around actual 0 are not masked. So remove this not. And now we get all of the values below 0 and 0. And let's say we mask to a height of 30 or 25, like so. And this just masks the transition area. Now we want to blur the mask, so append a Heightfield mask blur. Make it active and blur a little more, like so. And now we can use this mask to constrain the blurring of the actual terrain to the transition area. So put down a Heightfield blur. And you see that this Heightfield blur has two inputs. And the first input is the height, and the second input is the mask. But as the mask is stored in the same geometry stream as the height, we can use the same output port to feed the mask here. And then on the blur, you have this mask layer input, which specifies which volume to use as a mask. In this case, I want to use the predefined mask. And now I can blur this transition area here. And let's blur this quite a bit, like so. And you see that now the transition is really very smooth, which is important later on when we do the erosion. What is a little bit distracting with Heightfields is that this mask display cannot be deactivated easily. At least I did not find a way. So to get rid of this red overlay, I have to use a Heightfield mask clear. And now I can see what I did so far, and I have a nice blend between the hill area and the base area. To make this look a little bit more interesting, I will use a Heightfield distort now. This node basically advects the height information, so the pixel values, by a curl noise or a simplex noise you can choose. And here you have the amplitude, so if I up this, you see that this is moved around in the 2D image plane, like so. Don't overdo it, let's say 14, this is good, and this gives a little bit variation to my hills here. To make this look even more natural, let's erode it. So let's put down a Heightfield erode, and this is actually a solver, a DOP solver. So if I put this here, I get this visualization, which I can turn off if I like. Or I can set the range here in the visualization tab. I can click compute range, and then it stretches this gradient over the entire height range. It's good to keep this on because you see better what's happening. And if you press play, the actual solver is doing its thing. And it's solving for two things. It's doing hydro erosion. So this is basically rain carrying sediment with it. And this gives these valleys here. And then there is thermal erosion, and that is in nature the effect of rock breaking due to thermal effects and then being carried into the valleys. So two different effects that give very natural results. I let this run to, say, frame 36. As you can see, it's doing a very nice natural effect. But at the moment my terrain is very low resolution. And that is a good thing, because if this solver here is run on a very low resolution terrain, it forms very deep, large structures. And that is good for giving this whole environment the basic shape. Now I want to up the resolution and work on the details. But because I plan to do a second erosion later on, I have to somehow store this state, because otherwise if I run the second erosion, this solver will execute again. So one possibility is to export this as a BGeo and then re-import it, but a quicker way is to just lock this node and keep this current state here. Then it will be saved directly to the HIP file. But before we do that, let's make sure to deactivate the visualization, because otherwise it will be locked into this state and I don't get rid of the visualization later on. So let's lock this here as our initial state for detailing. Changing the resolution is easily achieved with a resample. Be sure to use a Heightfield resample node and just append it here. And it's very easy because you can just give a resolution scale. In my case, let's say 4, and then it will have 4 times the resolution. So now I have a 2000 by 2000 resolution, which is enough detail for my needs. And after that, we can go on with detailing. So I plan to add some terraces to the slopes of this world. So let's create another mask by feature and append it here. And this time I actually want to use a mask by slope. Let's go a little bit lower here with this value such that I really get the slopes. And I can use this to constrain the adding of terraces, which I do with the terrace node. Heightfield terrace. So connect this here. And what this does, it creates terraces, typical in certain geological forms. But it has this range here. And that means it only creates these terraces in a certain height range. So press the compute range button to first create these terraces all over the place, and then make the terraces smaller, a lot smaller, to have very little terraces. But you see that you don't see much, and that is due to this smooth here. If we go lower with this value, we have this stair-stepping effect, which we are after. And now let's constrain this to the mask that we created by putting the mask in the mask input. If we do that, we get terraces only in these areas here where the slope is steep, like so. And these terraces give a little bit more detail when doing the second erode. Before we continue, let's get rid of the mask again. So mask clear. Now you can appreciate the stair stepping, and let's add some more noise, Heightfield noise, just to make this a little bit more detailed before we do our final erosion step. This time I need a smaller element size, and the amplitude has to be a lot lower because I'm adding this noise to already given terrain. And if I now go to simplex again, you see that this gives me a little bit of detail here in these flat areas, as you can see here, which is giving a good input to the erosion. So now erode again. Before we activate it, make sure to go back to frame 1. Now activate the erode, you get the visualization back, and let's run the erosion. And you see now you are getting really a lot of detail here. Great, this is looking good. Now you have a lot of detail in your terrain. Let's lock this state too. Of course you can export it, but locking will do. And before we render, let's append a Heightfield visualize. Because the erosion solver not only creates the erosion of the height, but it creates some interesting mask layers too. Let's do compute range here. And this visualize node allows you not only to visualize the height with a ramp, but you can visualize all the other layers too. For example, the flow layer here in purple. And you see, this is generated by the solver, and it's a very interesting layer that you can use later on for texturing, for example. If you don't want to use flow, there is this debris layer, which is even more interesting, I think. These layers are very important for realistic texturing. Cool. But now let's render in Redshift. And to do that, we need a null, as we want to output this whole terrain. Let's call it out terrain. The problem is that Redshift does not understand 2D volumes. So if I try to render this, I get nothing. But what Redshift understands is images. And the good thing is that Houdini not only is able to procedurally generate geometry, but it can procedurally generate images. So with generating images from the volumes, we can feed the information directly live to Redshift without the need of baking out. Because of course you can bake out everything, but then you have to redo this every time you alter your terrain, and that is not very workable. So to get images from these volumes, let's put down a COP2net and dive inside. And inside here, we will get a SOP import. And what this does is, it fetches 2D volumes from SOPs and creates a COP image from them. So if I go here, I can specify out terrain, accept, and let's quickly switch to the composite view here. You see, I'm instantly getting a result. But it has the wrong aspect ratio, so let's set resolution from SOP, and this sets the resolution to 2000 by 2000 because this is the resolution of my volume. But as I showed you with the visualization node a second ago, I have many image planes in my volumes, or many different volumes. And I want to import these as different image planes here. So press the Set Planes from SOP button. It looks as if nothing has happened. But if you go to this menu over here, you see that now I have all the volumes as named image planes. So I have the flow, and I have the debris, and all of this goodness. The height looks a little bit strange because it's just black and white, but that's due to the high dynamic range. If you press this button down here, the display will be fit to the range, and you see all the shades of the height. Great. The only problem is that if you want to import this to Redshift, it cannot be named different than C, because the standard plane in COPs is C color. So you have to somehow get rid of all the different planes and rename this to C to be able to import it to your material network. So let's do this. First, append a delete operator. That works more or less like a blast. And now if I put here height, it deletes the height. So now I'm left with a mask, bedrock, etc. But if I go here to non-scope planes, I'm left only with the height. That's what I'm after, because I only want to have the height. But it's still called height, so append a rename. And this allows you to rename image planes. And I want to rename from height to C, because this is a standard that Redshift understands. And then just append a null to be able to link to this. Let's call this out height. Great. Now we have an image plane called C that stores the height. If I press this button again, you see all the information is in here. And this can be referenced directly from a Redshift material. That is a trick. So let's go up one level and let's go to the material context. Inside of the material context, we create a Redshift material builder. And let's call this terrain and dive inside. Inside, we need a Redshift material and connect the out color to the surface. And now we want to use this height here as a texture. So lay down an RS texture node. And now we can use the op syntax as with mantra to reference operators from anywhere inside of our scene. But we need to know the global paths. So let's quickly go to the object context again, and inside our Heightfield node and inside of the Cop2net. To me, the easiest way to find out the global path to this node is to use a Python shell. So go to Windows and then Python shell. And this window will pop up. And the cool thing is that you can drag any node to this window and it will give you the global path to this node. In this case, object, Heightfield, Cop2net1, out height. Let's just copy this string and close Python shell. And if I now go back to materials, what I can do is, in this texture sampler, I can go to the file name and state up and colon. And this will tell Houdini to use an operator directly. Behind the scenes, Redshift will convert whatever it finds here into a Redshift texture and store it on disk in a cache directory, but it does this live and it doesn't interrupt your work, so it's perfect. Just paste your string here, and now I have this OP colon and then the global path to the node. And now I can use this as a color, just for debugging purposes. Let's wire it to diffuse color for now. Great, but we need an object to put this material on. So let's go back to the object context and create another Geo node. Switch to the scene view. And I plan to have a plane here being dynamically displaced by Redshift using the live texture from the Heightfield. So let's call this grid, dive inside, get rid of the file node, and lay down a grid. And make this grid the same size as our terrain, so 1000 by 1000. And let's give it a little resolution, let's say 100 by 100, just to save some work from the dynamic tessellation later. Now we need texture coordinates, because we want to map a texture to this. So lay down a UV project. Connect this. And under the Initialize tab, initialize to best plane. If we now press space at 5 to switch to the UV view, we see that we have a nice UV texture. The problem is that this texture is starting exactly at 0 in UNV, and it's going to exactly 1 in UNV. And this gives artifacts while mapping in Redshift. So what we want to do is do a UV transform. UV transform. And we want to use this to scale this UV map down a little bit. Just a little bit. 0.99. But we want to make the scale happen from the center, so use a pivot of 0.5. And now we have a nice UV map, but centered and a little bit smaller than the full range, which avoids the artifacts. And now append a null and call this outGrid. Like so. And this is what we want to render. Cool. Space 1, back to scene view. Now we have the terrain and we have a grid. And we want to apply our material to the grid. But it does not show up here under the material context. And that is because you have to go to material and you have to specify this material flag here. That makes the material visible to this selector. So now I have it here under my mat. And I press accept to apply it. And let's do a quick test render. But before we do so, switch to the Redshift shelf. First, by control clicking on camera, lay down a camera. And lay down a RS light dome, such that we have a little light in our scene. And now we are prepared to do a first test rendering by pressing the IPR button. First, make sure to press the Redshift button to add a Redshift drop, like so. Back to Object, and now you can press the IPR button, which takes a while, and then AmPlay opens up. The Redshift scene is built, and you get this result. And this is actually good, because it worked. It actually pulled the texture from the COP2 context to the Redshift material context and put it here onto my plane, which is great. So debug mode worked, but what about the displacement? Well, the displacement should be straightforward. Switch to mat and cut this connection and create a displace, RS displacement, and connect this here. And this displacement will create a displacement for this displacement port. So now we have displacement. But before we can actually use the displacement, we have to switch to the OBJ context again, select the grid and give it object parameters, Redshift object parameters. And here under tessellation, I can enable dynamic tessellation because I want the grid to be tessellated before displacement, and I then can enable displacement. But be careful, because the maximum displacement is constrained to 1 unit at the moment. And our height is a lot higher than 1 unit, so if I render now, I don't get right results. So up this to, say, 100. Let's see if this is enough. And maybe go to the RS light dome and make it a little bit darker, maybe a little bluish, like so. And let's render again. And here you have it in all its glory. Right-click always on top, and you can see I now have my terrain displaced live by Redshift. And if I alter it, the changes are reflected immediately. The very last problem that is left is that the orientation of this does not match our height field. And that is due to the UV mapping. So quickly go to the grid and then to the UV project. And here under transform you see this rotation that is set by the initialize to best plane. And what we have to do is we want to rotate it another 90 degrees here in Y. And then we want to flip the X by putting a minus sign in front of the 1000, like so. And now we have exactly the same orientation as on the Houdini side of things. So now it matches and I can actually go here and have my view part in sync with my rendering. And for the textures, the workflow is exactly the same. What you do is you go to the COP2 net and create more layers with the individual masks, and then you can use all of this inside of the Redshift material and put texture layers on top of this. So, thank you very much for watching. I hope you learned something as always, and see you next time. As always, a very big thank you to all our patrons on Patreon, especially Mohamed Alabri and Joseph Howerton. Thank you so much for supporting us and making this all possible.